Okay, so today let's discuss the significance of statistical process control chart and the content of that. And I'm going to draw them myself today, and I'll ask you to follow along with me. The significance of statistical process control chart, and this is developed by this person, Walter A. Short, he lived between 1891 to 1967. And he's the person of statistical quality control during the World War II. And, by doing so, we understand what quality a process has, and we can visualize, we can see what is happening with the process. Anything going wrong or okay, that can be understood by this statistical process control chart. And there are many types of process control chart, and we are going to learn today one specific thing which can be applied to many other situations. It looks like this. So we have any process. For example, it can be a TD bank clerk. You want to see how many customers are coming in and how long does it take for the customers to go through their process, whether it be just simply depositing or withdrawing some money or having a consult session with advisor there, financial advisor there. Depending on the nature of the things, how does the process achieve the purpose that can be discussed in this process chart. And we understand whether it is going good or not by just simply looking at this chart. For example, you see that, oh yeah, we have this upper limit and lower limit and central line here, and we see that one spot is going out of the control. And what happened at the time? Was it special case, or was it a general case? Was it because we did something wrong, or was it because the customer was asking something extraordinary, right? Those things we can discuss and understand by drawing it. And we can also see, there's a trend of increasing the time limits. And, oh yeah, is that a general trend? Is it happening at this time only, or our process is going out of order? The same with the equipment. If you are working with an equipment and the equipment is doing very well, performing very well at first, however, as time goes on, it's going out of the control. And as a result, we want to understand why that went out of the control, right? That can be understood. And this is meaningful because now you can see the process. Before, you had no idea how the process is working out. However, now, because you have this statistical process control chart, you understand and visualize the process. And you can analyze it and do something about that. So that's the beauty of statistical process control chart, because you are understanding visually what is happening with your process. So advantages are you can monitor the process, you can correct the process, you can improve the process. Those are advantages of this process control chart. And it can be used in many cases. It can be used in manufacturing, doctor's office, or a food restaurant, quality satisfaction. If you have any process and measure that, you can use statistical process control chart. What is the content of statistical process control chart? There are a few things that you want to think about. What we are interested in is variance. Well, how much variance this process is creating? Do we have small variance or large variance? Is it something that happening naturally, or is it something that is attributed by a special cause? Oh yeah, the equipment is going out of control. It needs a lubricant. It needs to be recalibrated. Those things. Or the person is too tired and fatigue is attacking it. So those special causes we can also identify. So what is this variance about? Is it natural cause or special cause? And depending on the circumstance and investigation, we want to identify that, separate that, and if all possible, address the issue from the bottom. And sources of variance, again, there are natural causes and special causes. And special causes are something that we have to address, something that we aim to remove, that's a special source or special cause. However, natural cause, for example, um, uh, temperature changes all the time, and you will not be able to control those things. Or fatigues comes all the time, and how are we going to change that? And although I teach, sometimes I teach well, sometimes I don't teach well. Um, is it because of me, or is it a natural thing? So if there's something that I can identify the cause myself and remove it, then I can find it. But if it is just a small fluctuation, it may be just natural thing, and I may not be able to identify that. So we want to separate them together and eliminate the source of variation as much as possible. The second thing that we want to consider is mean versus range. We have two sources of variation. One variation comes from mean, and the other one comes from range. And I take an example of this. So let me share this. Okay, do you guys see this screen? Do you see my screen or no?
It's on the mean versus range slide.
So let me see. Let me stop sharing this.
Do you have multiple monitors?
Yeah, I have one tablet. I'm using tablet.
Oh, there it is.
See that? Okay, good. So let me show you. So I have 30 students. I'm a HR person. Okay, I'm a HR person, and I want to hire a person. So here is Mark, and here is Kevin. And I want to hire a person based on GPA only. And I want to look at operations management, finance, and also marketing. So three courses only. And I see that Mark, he got A from operations management, B from finance, and C from marketing. And Kevin got B from OM, finance, OM, and B from marketing. So, and I know the GPA for these three things will be 3.0 here and 3.0. So the question is, who to hire? Yeah. So here's a question. Anybody? Who would you hire if you are HR personnel person? Are you going to hire Mark or Kevin?
Kevin, because his variance is lower, so he's more consistent.
Okay. Was it Rocco?
Yeah.
Okay. Thank you, Rocco. So Rocco wants to go for Kevin. Anybody who wants to hire Mark instead of Kevin?
I think it depends on what the job you're looking to hire for is. If I'm looking for somebody in marketing, Mark would definitely not be the choice. But there will probably be more data on that. But if I'm looking for somebody specifically in operations management, then Mark looks like he's better at that in particular, where I wouldn't really need somebody good at marketing then.
That's a good point. So it also depends on the nature of the job. If the person is going to be in charge of operations, Mark might be a better choice than Kevin. If it is a marketing job, I think Kevin is a better choice. So also, if you are looking at a person with more consistency, then you may want to go for Kevin. However, if you are looking at more creativity than consistency, you might also want to go with Mark because you don't see much creativity with Kevin, right? So, but what I want to show you is that although the GPA is the same, there is a variance from the standard deviation, right? So although you have the same GPA, that does not mean these two persons or two processes are the same. But we usually go by average and we don't pay attention to variance. However, in operations management, variance is a very important concept, and we want to look at it and analyze it and see what kind of variance it has. So Kevin, variance is 0, right? So if you are looking at a person with consistency, I think Kevin might be the choice in this case. So we have two sources of variance. One is mean, and second is variance, standard deviation, right? So these two things that we are looking at, and although you might see that this is in control, however, standard deviation or range might not be in control. So when you are looking at a process, you have to check not only mean, but also process or the range together. So you have to look at both of them together. And then you can say, oh, this process is in control or is not in control. That can be analyzed only if you check both mean and range together. That's what I'm trying to say here. So then let me talk about two things. So now the third topic is mean chart and range chart. So these are the things that I want to talk about. And in mean chart, you have a few things that you have to do. So the formula for that is, so you are going to have mean chart and upper control limit and lower control limit. And here is going to be center line, okay? So upper control limit, lower control limit, and this is center line. And mean chart can look like this, right? So ideal statistical process control chart will look like this. So it oscillates around the center line, and it's ups and downs always like that. So this is a very ideal process. However, if you have a process like this, so it goes up and stays there, and then comes down and stays there and goes up. So you just add the dots and it looks like that. And this is not a good process because it's not oscillating. It's just staying on one side longer than the others. And it's close to upper control limit and lower control limit. So that's a not good process. It's a not stable process. You want to do something about this and you want to investigate it. Even if there's no point outside of the upper control limit and lower control limit, you have to do something about that because this is going out of control. So even if there is the case, even if you don't have any points outside of the control limit, you need to take a look at it. So both mean chart and R chart is going to have that, and we want to draw that and then visualize all together. And here is the formula for that. And it's not scary. It's not really difficult formula to use. And a mean chart is, we say, X bar chart. It's a mean chart. That's a mean chart. And mean chart is going to have upper control limit, and lower control limit, central line, and lower control limit. Okay, those are three lines that we have to calculate. And upper control limit will look like X double bar, not just X bar, but we have two bars, so X double bar plus A2 times R bar. That's upper control limit. And center line is simply just x double bar. And lower control limit is x double bar minus A2 times R bar. That's your formula for this. And there's a much more complicated formula. And this is actually used when sigma is unknown. Actually, this is the formula that we use. But for the sake of simplification, we are going to use this formula because it's straightforward. And where x double bar is mean of means, where x double bar is mean of means, and R bar is mean of range. And A2 is from table S6. So the table, I'm going to show you what that is. And R chart, let me do R chart now. For R chart, it's simpler. So we have upper control limit and center line and lower control limit. And upper control limit is simply D4 times R bar will be your upper control limit. And center line is going to be R bar. And lower control limit is D3 times R bar. So those are three formula, and where D3 and D4 are from table 6.1. That's your R chart, and we are going to draw that together. And let me show you the table 6.1. And here's the table. So we have table 6.1, and this is the table that management scholars built to calculate statistical process control chart. And these are factors for computing control chart limits, right? And it's 3 sigma. It's not 6 sigma. Not 6 sigma, but 3 sigma level, and covers 97% of that. And we have A2, D4, and D3. And for sample size, we need to say we have sample size of 8, right? And you read A2 value here, 0.373, and then calculate X double bar and R, and calculate that. So the corresponding A2 and D4 and D3 are right here, and just plug them in and calculate that, and you will find the values and control limits and center lines, and visualize the process. So that's how it goes. Let me take an example. Okay, so let me take an example. So if I just reinforce what I said, here, mean versus range, you see that in this process, the range is stable. The range between from top to bottom is steady, the same actually, right? So range is similar. However, the mean is changing. Mean is going upward, right? So if you visualize that on your statistical process control chart, it looks like this. It goes upward, and this one is out of the control limits. And the same with similarly, R chart, range chart is going to be staying the same because the range from top to bottom is constant. So it's staying the same. However, in this case, you look and the average or the mean is staying the same on the same spot. However, the range is increasing, right? From top to bottom, it's getting flatter, and that's problematic. So if you visualize it in your statistical process control chart, it looks like that. The mean chart is stable. However, our chart is gradually increasing. As a result, this is not a stable process. That's why you have to look at both X bar chart and R chart. Okay, so here's an example. I'm going to show you a video clip, and then we'll do a class exercise together. I'm going to show you this video clip. Uh-oh.
The volt is becoming very real, very fast. That's right, 230 miles per gallon, which is a very good number. My first reaction was, it's a good number, tell me how we do it. Calculate it, because we know how the vehicle works, but it's important to understand what's the yardstick, what's the measuring stick, because all manufacturers are going to be judged against the same measuring stick. And after satisfying ourselves that, we had done a good analysis, that it was a very good number, and we felt confident about it, today it is a very good number. We've had this ubiquitous, smiley electrical plug with a 2 and a 3 over the last 3 or 4 days. Actually, over the past week, people have been trying to figure out what it is. They've been beating a path to our doorstep, trying to get us to confirm. We held it up till this morning. I think Bloomberg broke it. But what it is under the federal test procedure, city fuel economy, we expect to be at least 230 miles per gallon. And composite, including city and highway, will be triple digits. Will be over 100.
Okay, so this is an announcement from Chevy Bolt saying that it's going to achieve 230 miles per gallon in city driving condition. So that was an impressive advertisement. And say you are producing Chevy Bolt in Detroit, Michigan, and you are a production manager, and you want to visualize this process and see how it is going. And that's what we are trying to do in this exercise. So let me share my screen again with you. Okay, do you see my screen? Okay, very good. So because it's easier for you to understand, if I just write it out, so that's what I'm going to do. So I'm hoping that you are going to follow along with me, writing this table and trying to visualize the process together with me. So I'm going to draw a table saying here Chevy Bolt. Chevy Bolt production. Okay, that's what I want to do. And I want to draw a table like that. And I'm going to have here start time. Go here, start time, and end time. And say I am running 3 lines to produce Chevy Bolt. So I'm going to say line 1 and line 2 and line 3. So I'm running these 3 lines, and the start time, say 9 a.m. I want to start, and then I checked at 10 a.m. and in line 1, it's Wednesday, and then say I produced 10 cars, 10 Chevy Bolts, and you tested the mileage per gallon and found that it's 200 miles per gallon you found from 10 sample cars of the line 1. In line 2, say they got 9 cars in 1 hour and their mileage per gallon is 210 miles per gallon. In line 3, you found it's 185. And similarly, you are going to do at 10 o'clock and 10 to 11 a.m. And you have done that. And in line 1, 210 miles per gallon and 215 miles per gallon and 210 for line 3. And do the same for 11 to 12. And you did the testing and found it was 180 for line 1, 170 for line 2, and 240 for line 3. And 12 p.m. to 1 p.m. you did the same thing and you found it's 195 here and 195 here and 200 for line 3 and 1 p.m. to 2 p.m. it's 205, 220, 180 and 2 p.m. to 3 p.m. 220, 205 and 210, 3 to 4, 3 to 4, you found 190, 200 and 210. Lastly, 4 to 5, 4 and 5, 200, 195 and 210. Okay, so it was a lot of work, but this is the practice in real business that they measure everything, and that's what you have found. So then, if you have this kind of data, then what you can do is that now we have to calculate X double bar and R bar and everything. So let's first start with X double bar. So I'm going to start with here X bar. X bar. Okay, so you make X bar. Let me use a different color. X bar. X bar, and X bar is simply the average of these three things. So 200 plus 210 plus 185 and divided by 3, that will give you the value. So can anybody, what is it? 200. What's the average? 200, 210, and 185?
198.3 repeated.
198.3. Thank you. And similarly, let's go for 210, 215, and 215. So that's going to be 5 divided by 3. It's 213.33. Is it right? Am I correct?
I got 211.6.
211.6. 211.6. Now 180, 170, 240.
I have 196.7.
Thank you. 196.7. The next one, 195, 195, 200, 196.6. Is it right?
Yeah.
Yeah, that's
Very
round
good.
up.
Yeah. 205 to 220 and 180. 201.6. Is that right?
Yeah.
Very good. 220, 205, and 210. So that I need your help.
211.7.
211.7. Thank you. Now 190, 200, 210. This one I know. It should be 200. 200, 195, 210.
201.6.
Thank you. So then x double bar is going to be the average of this. This is going to be x double bar. So let's calculate the average of this thing. So can somebody help me? So what is the average of these numbers? Anyone has the answer? Average of these x bars.
It's about 202.3.
I also got that.
Yeah, I got the same thing.
200.3.
202.3.
Okay, so we got, thank you, x double bar is 202.3. And then the next thing that we want to do is we want to find the R and R bar. And this is going to be R. R is range, and range is max minus minimum, right? That's easy. So if we calculate that, it's going to be 210 minus 185, and that's 25, right?
Yes.
25, good. And 215 minus 210 is 5. And 240 minus 170 is 70. And 200 minus 195 is 5. And we see 180 to 20, so 40. And 220 minus 205 is 15. And 210 minus 190 is 20. And 210 minus 195 is 15. And can you calculate the average of this? Okay, so what is the average of these numbers? So R bar equals
I got 24.4.
24.4. The same? You got the same answer?
Yeah, I got
I
the
also got the same.
Very good. Please. Okay, now then we can calculate X bar chart. X bar chart. I should delete this. We learned that upper control limit equals X double bar plus A2 times R bar. So we know that this is going to be 202.3 plus A2 times R bar. And we learned that that's 24.4. So let's find A2. And if you look at that chart here, so we have many sample size, 2 to 12, and mean factors are available there. So what do you think? What is the sample size in this case? Can anybody tell me?
It's 8.
The answer is 3. We have sample size of 3 because we have line 1 and line 2 and line 3. So there are 3 different lines. That's why we have 3 as the sample size. It's not because 9 to 5 we have 8 sessions, 8 hours, but it's because we have 3 different processes. That's why the sample size is 3. And the mean factor for that is 1.023, and D4 and D3 2.574. So I don't know if I can memorize that. 1.023 and 2.574. Let's go here.
If we were to calculate the means of it by line and then calculate the means of the 3 lines, would that more or less be the same thing as calculating it by time slots and then averaging all those means? Does that make sense?
I don't think so. They will throw you off. So 1.023 and D4, let me make note of that. I forgot already. What was it? Do you remember? Let me take a look at it. D4 was 2.574. 2.574. Okay. So can anybody use calculator and find what that is? So 2.3 plus 1.023 times 24.4. What is it? Do you have it?
It's 227.26.
I'm sorry, say it again, please.
227.26.
Thank you. 227.26.
0.26.
Very good. Now, center line is going to be x double bar. Is 202.3. Now, lower control limit is x double bar minus 8 times A2 times R bar. And that's 202.3 minus 1.023 times 24.4. What is it? So 170, 178, 177.
Yeah, it's 177.34.
Thank you. So then we can now visualize this. So look at that. So central line is 202.3, 202.3. That's your central line. And upper control limit is over here, and that's 227.26. 227.26. That's upper control limit. Lower control limit is 177. 177. 0.34. That's lower control limit over here. And we have time. And the time is at 9 a.m., 10 a.m., 11, 12, 1, 2, 3, 4. So we have this time, and we have, let me make it smaller and see what happened. So at 9 a.m., we know that's 198, and 198 is smaller than 202, so it's below center line. And at 10 a.m., 211, right? So 211. So I'm going to do 211.6. So approximately about here, 211. And at 11 o'clock, 196.7. So it's lower here. And then 196.6 is there. And at 1 o'clock, 201.6. So it's very close to the center line here. And 211.7 is at 2. So 211, it's near the point at 10. And 200 at 3 o'clock. And then 201.6, similar. And then I'm going to connect these dots myself. So I'm going to connect the dots. 1, 2, 3, 4, 5, 6, and 7. So that's my X bar chart. And X bar chart, I'm pretty satisfied with this X bar chart because it's okay. You know, it's not out of the limits, and it's just staying inside, and it's oscillating. It's not too close to the central limit, the upper control limit or lower control limits. So I'm pretty satisfied with that. But you should not stop here. But you also need to work on the R chart here. So this is X bar chart. And you have to work on R chart here. So for R chart, let us calculate upper control limit. That's D4 times R bar. And D4, I found that before, so 2.574 times R bar. R bar is given as 24.4 here, so 24.4. Somebody calculate this for me. 2.574 times 24.4.
It's 62.81.
Thank you. 62.81. And central line is R bar. That's 24.4. That's easy. Lower control limit is D3 times R bar. And D3 is 0 times 24.4. And that's 0. So we know that it's going to look like this. And upper control limit and lower control limit.
Excuse me, I just want to let you know the time is 1:25.
Oh, I see. Let me spend only 3 minutes to finish this up. So 9, 10, 11, 12, 1, 2, 3, and 4. And we have 25, 5, 70. 25, 5, 70. So look, this is 62, and 70 is right here, and 12 o'clock, 5, 40, 15. 40 and 15, and 20, 15, 20 and 15, and you connect them together. So this is going to be your R chart, and clearly I see that this is not good, out of bounds, and also it's fluctuating too severely. So I'm not satisfied with R chart. And in conclusion, I would say this process is out of control because R chart is not stable.